Assalamualaikum warahmatullahi wabarakatuh. So this is notes or lesson for DC motor drive using rectifier. And for your information, this DC motor can have two type of drive. The first one using the rectifier, and the second one using a DC-DC converter or chopper that we will actually learn in chapter 2. So actually for this part one, we recall back the structure of the DC motor, the principal operation of the DC motor, and so on. And then after that, we will go on how we can apply the rectifier to control the speed, torque, and torque of the motor. Okay, so actually for mechanical output, okay, we are using electrical input to control the mechanical output. So actually, for the electrical, we are always usually control the voltage and current, and the mechanical output. Always there are three output that we would like to control. The first one is the speed. Second one is the torque, and the third one is the position. But for this course, we only concentrate on how to control the speed and also torque for the motor. Okay, so this is the first part actually. In the first part, we will actually go for the introduction, the basic principle of the mechanics. I think this one we just go fast, and then will be more towards on quadrant of operations, and then the DC and AC motor, and then after that, then we will go on how to control the DC motor by using the what you call the rectifier circuit. Okay, so this is actually the typical system, the typical structure on actually how we can control the motor. Okay, so the DC motor speed. Actually, to control the DC motor speed is actually by vary the input voltage. So that is the what I call the most efficient way. So if you want to vary the speed, you need to vary the DC input. Okay, so this is the typical structure where how we can actually vary this DC is actually because we are using a what I call AC supply from the TNB, so we need an AC motor, okay, with a fixed speed, because we know the AC motor is efficient in the fixed speed, and then it is connected, okay, coupled with a DC generator, where this DC generator will actually generate a DC supply, DC voltage, and then to generate variable DC, what we need to do is actually by using the voltage division technique, where you vary the resistor value, so to get the desired DC. Okay, so this typical system is bulky, okay, because involve two generator. We have AC motor, and then we need to couple with the DC generator, and then it is actually inefficient because we have losses in this part, where we have a what I call the variable resistor here, and inflexible. Okay, so we want to remove this typical, okay, this typical structure here in the middle here with what we call this typical. Okay, so by using what we call rectifier. So we have the AC input, but at the output we have a what we call a DC output. Okay, by using the rectifier. So this is by using the power electronics. So very simple technique where we actually use a circuit, which is a either diode or SCR here, where the source is AC source. Okay, and then we have the motor, and then how to control the speed of the motor is just by using a sensor feedback voltage sensor and current sensor feedback to the control unit. You can either use a FPGA, DSP, or a microcontroller, and then this is the control signal come from your control signal here. So it will produce the signals, the switching signal for this power electronics, okay, to get the desired output speed and torque. So this is small, efficient, and also flexible. And the modern electrical drive with power electronics, so as you can see here, is actually applicable right now in the air conditioning. So if you have what I call the inverter system, inverter aircon, so that is where we have the power electronics. Okay, so actually this power electronics control the motor, which is this one is actually your compressor here. So this basic principle of mechanics, so I think I just go through, you can actually look at the slide, okay, which is, I think I just go through. Okay, and the most important part in this syllabus is to know what is what we call the quadrant of operation of the motor. So this is actually applicable for DC and AC motor. Okay, so we have what we call the 1 quadrant, 2 quadrant, and 4 quadrant. So what is actually the quadrant? So it's defined by the speed and the torque of the motor. So okay, so we can actually divide the quadrant by 4 regions depending on the sign of the speed and the sign of the torque. Okay, so if the speed is positive, so this is the speed is positive and the torque is positive. Okay, so this is called what we call forward motoring. Okay, quadrant number 1, and quadrant number 2 is where the speed is positive but the torque is negative. So this one we call forward braking. And the third quadrant is where right now the speed is negative but the torque is positive. Okay, sorry, the torque is negative. So this one is what we call reverse motoring. And the last one is actually where this one is the speed is negative but the torque is positive, meaning that this one is reverse braking. Okay, this one actually you can what you call represent it as what you call when you are driving a car. So when you are going forward, okay, going forward, meaning that the speed is positive, and the torque is actually you can represent just what you call the pedal, okay, the fuel pedal. So if you push, okay, push the pedal more, so meaning that you are going forward. So this one is a forward motoring. For quadrant 2 is forward braking, meaning that you are driving in the forward direction, moving forward, but you push a pedal brake. So meaning that you actually apply negative torque. So this one is forward braking. The quadrant number 3 is actually reverse motoring, meaning that you are in a reverse mode. So you are actually driving in reverse, and then you apply your fuel pedal. So meaning that you are moving faster in the reverse direction. While this one is actually reverse braking, you are in a reverse mode, and then you apply a brake pedal. Okay, so this one is very simple. If you can actually represent by using what we call when you are driving a car. Okay, so as mentioned earlier, the quadrant of operation is defined by the speed and the torque of the motor. And most rotating electrical machine, why it called machine? Because DC machine and AC machine, because actually DC motor can also act as a generator. Same case with the AC machine, AC motor. AC motor can become also just AC generator. So that's why always we are referring this DC motor and AC motor as also a DC machine and also AC machine. Okay, so actually all motors, all machines can operate in 4 quadrant, but the limitation is on the power electronics converter, the electrical circuit. That some of the electrical circuit, the converter, for example, the rectifier, cannot operate in all quadrants. So the limitation is on the circuit, not the motor. Okay. So this is actually relationship between torque and speed. So as can be mentioned here, the DC motor is very simple to control. Okay, because usually the speed and torque, the speed can be controlled by actually voltage and the torque can be controlled by the current. So if you want to increase the speed, you increase the voltage, and if you want to increase the torque, you can increase the current. Okay, so this one V out positive, this is also called also the speed. This one is also torque, so meaning that this one torque or speed is positive, torque is also positive, meaning that the voltage is also positive and the current is also positive. So the power, which is V multiplied with I, so both are positive, meaning that the power is actually supplied. Okay, while the supply by the circuit, while at this point the power is actually absorbed, because this one the voltage is positive but the current is negative. So meaning that the circuit absorb this power from the generated by the motor. So sometimes this one also called reverse braking, so reverse motoring and so on. Okay, so you need to also note this. Okay, so power supply, so this one is quadrant number 1, quadrant number 2. Okay, this one is quadrant number 3 and quadrant number 4. So quadrant number 2 and quadrant number 4, which is what called reverse. This is all reverse braking and reverse motoring. So meaning that the motor is actually supplying. The motor is supplying the power to the circuit. So I think this one maybe you are confused, because usually when P is positive, meaning that it's actually the motor. Okay, I think this one motor is actually absorbed. Okay, and this meaning that for the quadrant number 2 is actually supplying. Okay, this one is also absorbed. This is actually supplying. Okay, so when the motor is in the reverse, okay, so this one is actually you are supplying the power to the supply. So this one I think we just go through. So an electrical drive, as mentioned before, we can divide into two systems, which is using a DC motor as a prime mover, which is you are using DC motor as a mechanical output, and the second one is the AC motor. Okay, so the DC drive, so the advantage is that easy to control. If you want to actually control the speed, you just need to adjust the DC input. Okay, but for the AC motor, it's quite difficult, because to control the speed, you need a variable AC voltage, meaning that you need to have a variable magnitude and at the same time a variable frequency, which is in a typical system where the motor is directly supplied from the TNB. So the TNB is 50 Hertz. So it is very difficult for us to vary the frequency. Okay, the magnitude we can actually adjust by using a variac and so on, but the frequency is quite difficult. So this is also some what I call advantages and limitations of the DC motor and AC motor. So the DC motor, you need to have a regular maintenance, because it has a carbon brush. In terms of the structure, is also very heavy, expensive, and the speed is also very limited. But at the same time, it can be very easy to be controlled, because as can be shown after this, to speed is actually just controlling the voltage, and the torque is actually by controlling the current. Okay, but the AC motor has advantage in terms of maintenance. It also has a very lightweight, less expensive, and the speed can be operated in a very high speed. But the problem is on the control side. So however, okay, so as you can see here, during 1990s, the popularity of the DC motor is around 40%, but when we are getting to 2005, you can see the popularity of the AC drive is getting much more popular, because of even though the control is very complicated, but due to the introduction of power electronics, the control is no longer complicated. Okay, so that's why industry is moved forward to use AC motor drive instead of the DC motor. Even though the DC motor is very easy, but since the maintenance is quite high, so that's why industry move forward to the AC motor. Okay, so we go to the DC drive, the main part of this DC motor drive. Okay, the principle and operation and construction. So this is actually the structure of the DC machine, and that's why we call it machine, because we can operate as a motor and also as a generator. And at the structure of the DC motor, we have what we call the armature terminal and also the field terminal. So meaning that you need a power supply for both structure. So the armature is actually the rotor part, okay, and the field terminal is actually the stator part. So this is actually the structure of DC motor, which has two poles, meaning that you have north and south. Okay, meaning that the pair pole is one. So we have stator and rotor, and this stator we call field, while the rotor we call armature. So when we have a power supply connected to the stator, so we induce a flux, okay, and when also we have okay, when we supply rotor with a voltage supply, so it will also induce some flux also. Okay, so the interaction between the current and flux inside the rotor and also the stator, so it will produce a torque. Okay, so the rotation of the torque for this example is actually in the clockwise position. Okay, as the rotor rotates, so a voltage also will be induced in the rotor, and this voltage is known as the back EMF. So in order to look on how the speed is controlled on DC motor, so it's better that we actually build up, or we know the model, the electrical model of the DC motor. Okay, so this is actually the electrical model, the model of the DC motor. So this model makes us our analysis become easier, because from this model we can study the characteristic of the DC motor itself. So this is what we call the armature circuit, and this is what we call the field circuit. So armature circuit is the rotor part, and the field circuit, sorry, F-I-E-L-D. Okay, not field, F-E-I-L-D. Is it? No. Okay, F-I-E-L-D circuit. Okay, so this is the stator, and as you can see here, both circuit requires what I call power supply or voltage supply, and RA and LA represent the internal resistance of the winding, and LA is actually the inductance of the winding. LF and RF also represent the winding. Okay, and this one is EA. This is what we call back EMF. Okay, so when the rotor rotates, so they will produce some voltage, a very small voltage that we call back EMF. Okay, so from this armature circuit, we can actually derive the circuit, the KVL of the circuit here. So V terminal is equal to RAIA, the IA is the current armature, plus the L, the IA dt plus the back EMF. while for the field circuit is VF is equal to RF IF plus L DIF dt. So actually this field circuit is actually used to assist in the producing the torque. Okay, and this type of circuit, DC motor, is actually what we call separately excited DC motor. Okay, because DC motor has several types. We have series DC motor, we have shunt DC motor, we have compound DC motor, and we have also separately excited DC motor. So actually the separate excited DC motor is the most easiest DC motor type that can be controlled. So that's why we choose this motor to be used in our analysis. Okay. So, and then the torque, okay, as you can see here, the torque produced by the motor is equals to constant KT multiplied with the flux. So this flux is actually proportional to the IF. Okay, so that's why this field circuit is just helping the armature circuit in producing the flux. Okay, so flux IA. Okay, so the interaction between flux and IA will produce torque. So if this field circuit is not functioning, so there is no current IF flow, so there is no flux produced. So if there is no flux produced, meaning that there is no torque produced. Okay, and this is back EMF, where the voltage generated by this back EMF is proportional with the speed of the motor multiplied with a constant and also the flux. Okay, so if the field flux, okay, which is your field circuit, come from a permanent magnet, meaning that you don't need an electromagnetic circuit to magnetize the stator. So the motor is called the permanent magnet DC motor. So for this permanent magnet DC motor, the field current cannot be controlled, meaning that the flux is uncontrollable. Okay, so it is a constant. So therefore, since we cannot control the flux, so therefore the torque is controlled solely by the current, and the back EMF is solely by the speed. And most of the time, so as you can see, we have KT and KE. Most of the time, KT and KE is actually the same value. Okay, so we go for the speed control of DC motor. So as can be recalled back, the armature circuit has this equation. Okay, but in steady state, where the speed is constant, no change of the speed and no change of the current, meaning that this part di over dt is considered as a zero, so we can reduce the equation to this part, meaning that you have only RA, IA plus EA. Okay, so for steady state condition or steady state speed, we can actually expand these equations to this, where we have what we call speed and also torque as our variable. So when the KT is KE, so we can actually reduce this equation to these equations. Okay, meaning that from these equations, there are three possible methods to control the speed. Okay, the first one is by controlling the V terminal, which is the V input. The second one by controlling the field flux. So this one if you are not using permanent magnet. And the third one is by using the RA. Okay, there are three possible methods to control the speed. Okay, but usually the first and second method are not preferable. Okay, why? Because there are some that we discussed, some limitations. So mostly the speed is controlled by controlling the voltage input. So this is actually by varying the VT, what happens. So this is actually the characteristic. Okay. the characteristic of speed for voltage number 1, for example. Okay, when you actually reduce the voltage, you have a different characteristic. Okay, so you have a different speed, no speed, okay, no load speed, and so on. So this is when you have voltage vary. Okay, but as you can see here, so this is actually the no load speed. Okay, this intersection, what we call no load speed. Okay, and then this line is what we call torque load. The intersection between the motor characteristic and your torque load characteristic is where your motor will actually operate. And this is what we call this full load speed. Okay, so for example, this one 500 volt, so this one 400 volt. So we have different characteristic depending on the voltage input. Okay, so as you can see, we can actually this is what we call the difference between no load speed and the full load speed. Okay, and then as you can see, when we are using the VT, the difference between no load and also full load it's not a very big difference. So that is one of the important parameters or important point that we want to control. We don't want the difference between no load and full load to be very big. Okay, so this is the intersection where this is the speed, okay, for different input. Okay, but the problem with this technique, this is actually the most efficient way to control the speed, but it requires a variable DC supply, where in the past few years it's quite challenging to have variable DC supply because we don't have the power electronics at that time. The second one is by varying the RA. So as you can see, by varying the RA, this is your no load speed, and if you increase the resistor value, you will have a different characteristic of your DC motor, and this intersection will give you the speed. Okay, the speed of the motor to operate. So as you can see here, if your resistor is changed, is increased, the difference between no load and full load will be very big. Okay, for example, if you increase further, your no load and full load speed difference is big here. So it is a simple control because you are just varying the RA, but you have what I call losses. Okay, and at the same time, the difference between no load speed and full load speed is very big. The second one is by varying the flux. So by varying the flux, not possible, this one, not possible for the permanent magnet, because permanent magnet is a permanent magnet where you cannot control the flux, okay? But if you are using what I call electromagnetic system, where you need to magnetize the stator, okay, so you can actually control the flux, okay, but this problem is actually, you will actually reducing the torque capability of the motor. So actually, the most efficient way is varying the voltage input, and that is how this is possible by using what we call power electronics. So this is actually the overall system. If you are using, if you have a three-phase or single-phase AC supply, so this system is a three-phase power supply. As you can see, we can actually have a variable DC voltage at the output by varying the firing angle. So this is the three-phase. Okay, so the DC output is actually, by if you are using three-phase rectifier, you can use this equation. Okay, and as can be seen here, so we have two circuits, and these two circuits need power supply. So you can actually share these two power supply, or you can have a separate power supply. Okay, so you can actually control the IF, or meaning that if you control the IF, meaning that you control the flux. Okay, so by actually adjusting the firing angle. So that is how we can control the speed and torque of the motor by actually controlling the rectifier. So this is same, okay. So this is for the single phase. So for the analysis, we are assuming that the current to be always continuous. Because why continuous? Because the LA is usually very large compared to your RA. Okay, so we assume that your motor is operated in continuous conduction mode. Okay, and so if the current is continuous, so the output of the rectifier, control rectifier, can be derived as this equation: 2 Vm over pi cos alpha. Okay, so VA is assumed is actually a DC voltage. So all the what I call equation is actually a DC circuit here. So and then the IA is a DC current also, because L is very large compared to RA. So we assume that the current is also DC. So based on the KVL, so VA minus EA over RA in a steady state, because inductor is short circuit in the steady state. Okay, and for the field circuit here, the VF can be controlled by controlling the firing angle of the circuit here. Okay, but you may see that this rectifier can only operated in 2 quadrants only, which is quadrant number 1, quadrant number 2. So speed positive. So if the speed is positive, so V positive and also I positive. Okay, and quadrant number 4, where the V is negative and I is positive. Okay, so this circuit is limited to only 2 quadrants, which is the forward motoring, okay, and reverse braking. Okay, forward motoring and reverse braking, meaning that both current are positive. This circuit cannot allow the current to be negative. Current negative meaning that the current is going back to the supply. So this is I negative. I positive is actually the current is going to the load. But if the current is negative, meaning that the motor is actually, the current is going back to the supply. So this is not allowed because we are using the SCR. So SCR is a unidirectional device where it only allows the current to move from anode to cathode. So that is the limitation of using this circuit. We only can use the motor to operate in either in forward motoring or reverse braking. The voltage positive and voltage negative can be obtained by adjusting the alpha, okay, beyond 90 degrees. Okay, so if you have cos alpha beyond 90 degrees, for example, cos 100, so you will have a negative value. Okay, so to have a negative voltage is possible because if when you adjust this alpha, but the current is not possible to be changed from positive to negative because the SCR is not allowed. So this is when you are using a three-phase source. So three-phase source, so what you need to do is actually to know that the VA here is a 3 multiplied VM line to line over square over pi cos alpha. Okay, and the armature current here is the same. Okay, it's a DC circuit here, so the same equations. And if you are using the field circuit using a single phase, then you can use this equation. So actually, DC motor is actually bidirectional, meaning that the current can positive and then the current can be negative. But the problem is actually on the rectifier itself. Okay, so however, if the rectifier is fully controlled, it can be operated to become a negative DC voltage. Okay, so this one is okay, negative. So and if you actually you can make your DC motor operated in full 4-quadrant. So it can be achieved by actually making a reversible circuit here. So this is actually how we can actually use a drive or reverse circuit, okay, to actually operate your motor to be in full 4-quadrant operation. Okay, so this is one of the circuit where you have this circuit to be operated, this circuit, okay, operated for this one, and this circuit operated for this one. Okay, so example we will continue on the next video. So thank you very much.